Hello, everyone. Good afternoon, good morning, or even good evening to some of you. We're very happy today to have Professor Wenwen Li and her PhD student Yuanyuan Tian to give us a talk on the KnowWhere knowledge graph. And for myself, I really want to thank the Semantic Harmonization cluster of ESIP for allowing us to use their regular meeting time for this talk. Let me give a quick introduction to Professor Wenwen Li and Ms. Yuanyuan Tian. Dr. Wenwen Li is currently a professor in GI Science in the School of Geographical Science and Urban Planning at Arizona State University. Her research interests include cyber infrastructure, geospatial big data, machine learning, and their application in data-intensive environmental and social sciences. Wenwen is a co-PI on the KnowWhere knowledge graph work. I think many of you are interested in the project. And then Ms. Yuanyuan Tian is currently a PhD student with Dr. Wenwen Li at Arizona State University. And she's also a member on this project. Okay. They're going to talk about KnowWhere knowledge graph and also the application of it in disaster response and humanitarian aid, providing the right help to the right people at the right time. So next, I will give the floor to Wenwen and Yuanyuan. Yep, it's your time.
Thanks, Marshall. Thanks very much for the introduction and invitation. We were very excited to give a brief introduction about our project and specifically the ASU side of research on disaster response and humanitarian aid with the knowledge graph. So Marshall told me that this group is quite technology savvy. So I'm trying to be a little bit more technical also. Just very briefly about what is a knowledge graph. I think many of us are familiar. Knowledge graph is composed by an ontology, which is also known as a schema, which can be considered as a data structure for our graph. And then the knowledge graph itself is an instantiation of the ontology with real data. So the building blocks of a knowledge graph is triples. So basically composed of subject, predicate, and object. And each of these triples is a fact. And then the interconnected facts compose as a knowledge graph. So by this is just a citation here. By May 2020, Google's knowledge graph contains 5 billion of entities and over 500 billion facts. And they are supporting 1/3 of the 100 billion queries made to Google each month. And this knowledge graph has also become a backbone to advance the GeoAI research, the geospatial artificial intelligence, by providing this knowledge guidance. And a little bit about the KnowWhereGraph project. It is an NSF-funded project in the Convergence Accelerator program. We started in 2019 for phase 1, which is a 1 million grant. Dahlia is also a partner on this project. And then after a year, we put a proposal together and compete for phase 2, which is a 5 million 2-year award. And we were very lucky to get it. And this project has 5 PIs, and the lead PI is Christopher Yuanyuan from University of Vienna and also UCSB. So the goal of a KnowWhereGraph, we are trying to build a large-scale knowledge graph for enabling geospatial intelligence. And there are 2 main use cases for this project. One is disaster response and humanitarian aid, which is also what ASU is heavily involved in. And another one is the food environment and supply chain, which this use case was led by our industrial partner, Oliver Wyman. And in building this KnowWhereGraph, one of the differentiators is we want to enable the know feature. So basically, how to make the graph to know more knowledge. So we are doing this by cross-link and integrate the cross-domain data set, information, and knowledge. And we are also working really hard to enable the capability for quickly assemble real-time data. And another prominent feature of this project is to enable KnowWhere, which is also a difference between other general knowledge graph projects. So by enabling KnowWhere, I mean, it should know what's happening where, so it can answer spatial queries and also support spatial reasoning. And this is a KnowWhereGraph team. We have a very large team with participants from academia, industry, government agencies, and nonprofit organizations. And my PhD student, Yuanyuan, who's a co-presenter today, has also been working really hard on this project. So when we started this project, there are overarching research questions, but 3 research questions that is of my interest, my team's interest are the following. And I would like to touch base on each of them today, and hopefully we will have more time in the future to communicate on these exciting topics. So the first is, what is the most reliable, scalable, and efficient semantic data repository? Because we are trying to build this large knowledge graph, and we need a data repository to store this graph. For example, the current KnowWhereGraph has about 13 billion triples, and how we can efficiently store and manage this large graph data. So that's our first research question. And the second one is, how can we construct a knowledge graph that can know where? So what is the essential role of location in building this graph? And the third question is how to develop a decision support system that leverage KnowWhereGraph and the geovisualization for disaster relief and humanitarian aid. Because after we build a graph, we really hope that it can use to support critical applications like a disaster response. And the graph itself, well, it's actually very complicated and it's very difficult for our stakeholder or the relief expert to use. So we need a way to convert this complex graph data to present it in a way that is more easily understanding by our end users. So the first question, how to enable the KnowWhere feature of the graph? So basically, we need to enable spatial queries and reasoning in terms of the topological relationship query, like whether A contains B, or whether A covers B, or A meets B. So these are the topological relationships. We cannot hardware all these spatial relations in the graph. We should have a way of dynamically find the relationships between 2 objects within the graph. So this will need the backend data repository to have the ability to conduct these spatial and topological queries. And another type of spatial query and reasoning is geometry operations for spatial analysis. Like if we need to know the intersection. What is the intersection geometry of 2 entities? Or what is a buffer of a certain areas or polygon? So these are the spatial analysis capability we are hoping the semantic data repository can also support. So in order to answer this question, we are investigating different types of semantic repositories to check and validate their efficiency and capability for handling big graph data and also handling spatial semantic queries. So there's 3 types of classes, 3 types of semantic repositories we are testing. The first type is the triple stores. So we have reviewed these 5 kinds of triple stores, and the highlighted ones are the ones we use to conduct experiments in the paper. So Blaze graph is also very popular one, and it has been used to support very large triples for wiki data. But upon our investigation, we found that it supported very limited spatial queries. So, so we didn't use that for the experiments. And RDI4J and the FuseKey both are open source triple stores, and the GraphDB and the Virtuoso are commercial ones. And it also has the free version for download. And another type of semantic repository is the property graph database, like Neo4j, which has become quite popular and different from the triple stores, like to store it in a triple, like Hurricane Katrina landed in Louisiana, and it converts triples to tuples. So for instance, for this triple, it can also add an additional property about when it happened to the land-in property. So this is how the Neo4j can further support adding more constraints. And a third type is called ontology-based data access. We investigate an open source solution called OnTop, which I really like this solution because it leverages spatial database at the end. So all the geospatial data doesn't need to convert to a graph format. Instead, they can reside in their native format. And then on top, add a semantic translation layer, basically to build a virtual knowledge graph by converting Sparkle queries, like semantic queries, into a database query. And then the returned result is also converted back to a semantic web format. So it really keeps the native structure of the geospatial data. So what we did is we performed the experiments on spatial and the topological relationships on all the highlighted triple stores. And we found that GraphDB, Virtuoso, and OnTop performs the best. And here I'm showing you their performance for a few of the non-spatial queries. So this is a complex query, but it's a non-spatial, so it's purely semantic. So we are trying to get all the SUGO unit. SUGO is Soil Survey Geographic Database. So we are trying to get all the SUGO units with the area less than 500 square meters. So this is semantic only query. And then this query is a complex spatial query. So both the spatial and the semantic. Like we are asking to return the average distance between grocery stores and their closest road network. So basically, this is a query about the accessibility. And in terms of the query response time for this semantic query, like we are getting the SUGO dataset, Virtuoso performs the best. So it has the fastest response rate. And then it's a GraphDB, and then it's the OnTop. But for the spatial related queries, we can see Virtuoso again performs the best, and then followed by OnTop, and then followed by GraphDB. So we analyze the reason we think the best performance caused by Virtuoso is because of two reasons. So first, it is written by C, so it's highly efficient. GraphDB is written by Java. And Virtuoso also has its native database, which supports this spatial queries quite efficiently. And OnTop, as I mentioned, which works also quite well and better than GraphDB. And it's like a virtual knowledge graph based concept has the potential of keeping all the geospatial data in their native format. So we don't need to convert the data all to the graph format and losing their original structure. And so this is our comparison. We think that although the OnTop didn't perform the best, but it really has a greater potential if we can further improve the kind of the translation layer from semantic to spatial query. And then once we identify the best triple stores, and we are trying to leverage the knowledge graph to support smart disaster management and humanitarian aid. So before we build our knowledge graph, we need to know what kind of questions are critical to answer so we can prepare the data accordingly. So take a hurricane as an example. After it happens, we want to know what is happening now, and also what has happened here in the past, and to whom it is happening. Like, who are the most vulnerable people, and how many people were or have been affected. And then what are the consequences? Because after the aftermath of the hurricane, it's not just the high wind that will cause damage. It also has a cascading disasters like flooding or a storm surge that will cause a lot of the damage to the property and also human lives. And we also want to know what are the risks. Is there any health risk to the communities after these disasters? So after having all of these questions at hand, so we are starting to collect this information from multi-source data and build our KnowWhereGraph to support this use case. And I will hand it to Yuanyuan.
Yeah, so you can hear me, right? Yes. Okay, good. So now there are a lot of questions to be answered, but there's no existing one single data set that covers all the information we need to answer those complex questions. So we need to integrate multi-source data. The table here gives you an overview of the data sets that we use for the disaster relief use case. But remember that the KnowWhereGraph project is a pretty big project, so we've acquired way much more than what you see here. Basically, there are two categories: thematic dataset and place-centric dataset. So thematic datasets includes hurricane tracks and the hazard data from NOAA. This provides us with details of storm trajectories and disasters' impacts over decades. And we also incorporate socioeconomic data from the US Census Bureau as contextual information and public health data from the CDC to understand community vulnerabilities. And the data on public health facilities is from Homeland Security. And we built a data set of experts generated through machine learning analysis of scientific publications, and we provide those authors based on their domain expertise. Another very important category is on the right side, that is location data. So weather zones are from NOAA and physical geographic features, including natural and man-made ones, are from USGS. And the location data is very important because we combine it with administrative division data so that we know what exactly happened in a specific place. This integration not only enriches our understanding, but also significantly enhances our disaster response capabilities. Next slide, please. So how do we manage and interpret the wealth of data? We developed an integrated ontological schema. So here we leveraged some existing ontologies because don't reinvent the wheels. So for example, here, ontology SOSA, that is for sensor, observation, sample, and actuator, is used here. You can see there are a lot of green boxes. There are SOSA classes. So they fit pretty well because most of our data is from sensors and can be, or it can be considered as observational data. So central to this schema is a use of geographic information, and it is used to link diverse data sets. Next slide, please. Yeah, so here, location ontology plays a pivotal role here. We created this class location boundary, and it comprises subclasses of geographic categorization, such as weather zone and administrative region. So here, the adherence to geospatial standards allows us to precisely define the geometry of location data like polygon, so we can embed geographic information to support spatial analysis. So, when people are building a knowledge graph, they usually talk about millions or billions of triples or entities, but really the point is that when you get a query, you want your graph to have the capability to return data that is traceable and information that is explainable, and also makes people feel that it is relatable, so that they know where to take actions. And the notion of place can be a very good helper when digesting what you put on their table. Okay, so yeah, I finished my part. Give the stage back to Wenwen.
Yeah, thanks, Yuanyuan. And after we defined ontology, our students have done a lot of the hard work of converting the data set into this graph schema, and then to generate our KnowWhereGraph. And then after this graph has been built, all the data has been integrated and converted into the graph format. So as I mentioned, this is a very complex graph structure, which is not very user-friendly. And if we want our decision makers, our stakeholders, and also the relief expert to make use of this knowledge within the graph, we need a better way of presenting our information. So that is the solution we have developed of develop a knowledge graph powered cyber infrastructure. So once a use case has been given, like a hurricane, we first understand the needs of data, and then we retrieve all the relevant data, and then build an integrated ontological schema for that. And then we converted all the data to generate the knowledge graph, which this part Yuanyuan has introduced. And then the next thing is how to enable and develop a cyber infrastructure to conduct a visual analytics of connecting and demonstrating all this relevant information in a user-friendly way. So what we did is we decompose the disaster relief workflow into several steps and several scenes, visual scenes. So for instance, after hurricane has passed or are moving toward the mainland, the first step is to identify the physical properties of that disaster, like the wind speed or the categories of the tropical storms. And then we can develop a query and get the subgraph that has the needed information for us. And then the second step is we want to investigate the historical impact, because the communities which were vulnerable for past disasters are most likely to be vulnerable toward the future disasters. And then we want to gain an insight on the spatial, demographic, and the social context, and also in terms of the health profile, because a lot of people, if they have the health conditions and after a disaster happens, there may be power outage and their medicines cannot continue being cooled down, and they need to go to some health clinics to get help for their medical supplies. And we also want to find the expert, which has the desired expertise to support and guide the relief expert. So all of this information we are trying to grab the specific subgraph in order to show the needed data set. And so the scene-based visualization is actually used to embed the emergency response workflow into this visual analytics to help make more informed decisions. And in our solutions, we have applied the multiple filtering techniques, like we can filter the damage caused by different disaster types, and we enable temporal filter, the scatter plot-based filter, spatial-based filter, just to helping people to better understand, to develop situation awareness for the disaster-affected region. And we also enable the expert search and the filtering. So here I want to show the portal that we have developed. If you are interested, you are welcome to get into the live link to interact with our system. And in this current interface, you are seeing the landfall locations for the 10 deadliest hurricanes in the past 50 years. If we click the drop-down menu, we can see all the disaster information and their physical parameters, like what's the category, what's the max wind speed, and the minimum pressure. And if we can also do a search based on keywords. So this is Hurricane Harvey, which is a hurricane type category 4 hurricane. And we can load their trajectory information, and this circles shows the affected areas based on wind speed estimation. And we can also show the consequential impact by Hurricane Harvey, because after the hurricane has passed the mainland, the different counties may have the report about the disasters or damage. So here are the information you are seeing is caused by, it's a different damage report. So what we are seeing now is a property damage, and we can also see what are the crop damage, indirect deaths, and other information. And basically the higher values is placed in red. And we actually also provide so this shows the direct death information caused by Hurricane Harvey. And we can also show injuries and other type of information. At the same time, we have also provided the health profile in this local regions, like diabetes rate, mentally unhealthy days, because after hurricanes, those more people may be affected both mentally and physically to this disaster. So we want to identify where are the most vulnerable communities. And so besides that, we can also filter the damage by different cascading class disasters like flash flood, hurricane, tropical storm, storm surge, and other type. And at the same time, our scatter plot will actually help us to filter out where are the vulnerable communities which suffer from, for instance, high diabetes rates and high property damage. So by drawing a box of interest on the graph, you will be able to see, okay, so these 4 or 5 counties suffer from high diabetes rates and also high property damage. So those are probably the areas where we want to allocate more resources to help. So this is the past event. By flash flood, the property damage is $1.5 billion US dollars. And then in terms of the health profile, we can see the adult obesity rate is pretty high. It's about nearly 50%. So those are the communities. By this joint analysis, we identify those communities to hopefully allocate more resources to help. And we can also enable to help the expert and expertise. As Yuanyuan mentioned, we generated this graph information by machine learning from a lot of the literatures. So what we did is we enable a search for the expert both nationally and also locally, because the expert with local knowledge is very important because they know the health clinics conditions, the capacity, and all kinds of information which is not readily available for the non-local expert. And if you are interested, you can also view the basic information of the expert. So those are the people that our collaborator, like Direct Relief, are trying to contact and get guidance about how to allocate those medical supplies after the disaster. So as a quick summary, so what we have been doing is we are leveraging our technology to create social benefits and by delivering the right help to the most needed people. An example, what we did is for Hurricane Ian's disaster response, like after Hurricane Ian is formed in the ocean, what we did is we quickly assembled and integrated its real-time path into the system. And then we can get approximately affected areas and load this health profile for this region to help our collaborators to identify the vulnerable community. And we also developed this novel visualization algorithms. So we place the graph on the map to better show the relationships between a disaster and also the underground impact. So what we want to do in the future is to integrate this cyber infrastructure and the knowledge graph to create the global impact for emergency response. So this includes to expand the current knowledge graph to include other disaster types beyond hurricane. And we also want to cover more international scope beside the US. And so this we'll also plan to include the global health hazards and also global health infrastructure in case of the future like epidemic and the pandemic outbreak. And one of the very important work, which is also ongoing right now, is we cannot build this knowledge graph manually. In the era of big data, there has to be some automated approach for doing that. And we are experimenting the AI-based automated knowledge graph generation approach. So this is an ongoing work which is under revision right now. So what we did is we used the natural language to infer the most suitable spatial relationship terms to complete the knowledge graph. So for example, different people from different countries, different culture, they may use different terms to connect different entities. Like for rivers, we normally will use flow through or flow into, and then for roads, we use intersect and across. So we developed this joint knowledge graph embedding and the link prediction approach where we consider different types of geographical entities, like it's rivers or road, and the multi-expressions by different people from different culture and the linguistic conventions, as well as the multiple relationship patterns. So our preliminary result shows our link prediction, basically for completing the knowledge graph, has shown very well for the long tail entities. Here are some example results, like Mississippi River is at the head of this long tail distribution because there are a lot of these entities called the Mississippi River in our generated knowledge graph. And then after this knowledge graph embedding, this is the predicted relationship between this Mississippi River and this entity Minnesota. So we can see using our proposed approach, it can find the relevant spatial relationship pretty well. But what is even more exciting is for the entities which at the tail of the long tail distribution, like Croix River and Minnesota, there are only a few entities in our knowledge graph. And then using this joint knowledge graph embedding approach, we can actually find more relevant spatial relationships that quantify the relationship between these two entities than the general knowledge graph embedding approach. So these are some of the preliminary results we want to share. And thank you so much for your attention and opportunity. And I would like to thank the KnowWhereGraph team and our PhD student for their very nice and hard work. Thank you.
Yeah. Thanks a lot, Wenwen and Yuanyuan, for this wonderful talk. Very impressive research and the results. We do have time for comments and questions. Anyone wants to go first?
Yeah, Wenwen, I had a question about Hurricane Ian. Did I understand correctly that you were actively engaged as Ian was coming and trying to predict where the impacts might be? And I was wondering if that's the case, have you followed up to see how well your model did based on data that you gathered after that?
Yeah, well, this is a very good question. First, we didn't do the post analysis. So what we did is we integrate the real-time trajectory prediction from NOAA. So they have a potentially affected areas. So what we did is once we get that affected areas, we can directly load this health profile information covering the approximate affected areas. And then our collaborators, the relief expert, can look at this health profile in terms of which regions may be affected and then identify the vulnerable communities. So in terms of prediction, I think we are mainly rely on NOAA's prediction instead of using our own. But what we are trying to help is once we know the approximate region people may be affected, and then we can help the relief expert to identify those critical communities to deliver help for.
Thanks, Wenwen. Next, Doc.
Hi, thanks. The very nice presentation, and just had a couple questions, kind of follow on what you're talking about there. When you're talking about, and in particular broader in terms of data integration. So you spoke about, quickly assembling data into the system. You talked about your kind of ML-based approaches to data integration and things like this. But one thing I was thinking about this is that some sources of data that may be able to feed into this would benefit by an a priori knowledge of what makes their data easily integrated into such a system, right? And of course, typically in a semantic environment, that would be something like providing shackle or checks or other types of kind of shape, approaches doing that. One, my question was, have you thought about that in terms of providing information to allow people to more quickly or to a priori manage metadata that they can express in an RDF vocabulary that aligns to those shapes? And two, if you could talk a little bit more about the types of operations, or if you have some documentation on the types of operations you do to integrate things like the hurricane trajectory and things like that into the system.
Mm-hmm. Yeah, I think this is another hard question. So what we did in terms of integrating multi-source data is basically use inspired research. We don't just go there to get some data and then convert it to the graph and then think about what this data can answer for us. So instead, we started from our questions, like we work closely with our relief expert to see what are the critical questions that they need to answer. And then what are the critical data resources that can help to answer those questions? And then we go to find the data, and then we build a schema, and then we try to answer those questions. So it's completely use-inspired and use case-driven approach.
I just wanted to say that it's kind of like if there were resources available, like Shackle, like Shex, like others, that allowed someone to know a priori how to facilitate integration into the system, you might find groups like the UN disasters group and things like that working ahead of time to enable that kind of rapid integration and utilization in the knowledge graph. And I would also, as you talk about going global, make a reference that you might look at some of the work that the United Nations is doing, and UNESCO in particular, in terms of disaster response, might be aligned very well with the direction that you're going.
Yeah, I think this is a very great suggestion. And if we can build a pipeline of connecting to those agencies which have already do some preparation in terms of some disasters, and then quickly connect to them and grab their information and integrate into the system, then it will really becomes more powerful and efficient. Thanks for the suggestion.
Yeah, no, very nice presentation.
Yep. And Kate Rose also pasted a question in chat. Do you want to ask it in person, or I can read it for you, Kate? Okay, I probably can just read. Have you tried to integrate real-time power outage into the KnowWhereGraph?
We did. We think this information is very important. But I forgot why we didn't. Yuanyuan, do you know?
Yeah, I remember. I think it's because of the data. As we didn't find a really good data source. I think we found a website, but that is like one person built that website. So at the end, we didn't incorporate this outrage data.
Great. Okay. I probably have a follow-up question. Probably is the last one. I think you already mentioned a lot of those temporal information in the knowledge graph and also application. So I think it's not, for the whole work, it's not only know where, it's also know when. But my question for you is, have you tried to incorporate, for example, the W3C time ontology or part of it in your knowledge graph and the application, and any work related to temporal topology?
I think this is a very interesting question. You know, we call our graph KnowWhere, and we really emphasize the importance of location and spatial analysis and spatial reasoning in the graph. But when we talk about time, we consider time as another attribute similar to a non-spatial, like just a regular attribute. I think we did incorporate time into it. We inherit some of the entities from W3C times in terms of building our integrated schema that Yuanyuan has showed. And then when answering this question, I think the non-spatial knowledge graph or semantic repositories can answer these temporal questions as a general non-spatial queries. So I think this is a very interesting suggestion. Why we didn't lift this problem to spatial temporal, but also only emphasize spatial, I think it's a good question for us to think more about.
Thanks for the Wenwen. So thinking about time, I think we can stop it here. I will stop recording.